They came back from Uranus with 6 hours of usable data and a problem they could not explain. It was January 1986. Voyager 2 was traveling at 14 kilometers per second when it crossed the magnetosphere of a planet tilted 98 degrees, a planet rolling sideways through its orbit like a coin that had stopped spinning. The probe's instruments flickered. The magnetic field readings were wrong. The field was offset from the center of the planet by a third of its radius and tilted 59 degrees from its rotation axis. The team thought the instrument was broken. It wasn't. We never went back. 40 years later, every textbook image of Uranus is built on those 6 hours of confused data. And now, NASA is racing to launch a flagship probe before a 2032 launch window closes forever. That is where this story begins. Not with curiosity, with a deadline. The reason NASA is finally going back to Uranus is not because the planet is interesting. It is because Uranus is the single most anomalous world in our solar system, and the gap between what we measured in 1986 and what our physics says should be possible has stopped being academic. The 2022 Planetary Science Decadal Survey ranked the Uranus orbiter and probe as the highest priority new flagship mission in the United States. Not Mars, not Europa, Uranus. The mission that has been deferred for 4 decades is suddenly the one that cannot wait. The cruise time alone is 13 years. If you are watching this in your 40s, you will be in your 60s when the data arrives. If you are in your 60s, you may not see it at all. This is a generational commitment to fix a 40-year mistake, and it is being framed in press releases as routine exploration. It is not routine. It is belated triage. The planet we ignored is the one we understand least, and the bill on that ignorance is now due. The official story is that we are going because Uranus is interesting. The real story is that the last time we looked, the data did not make sense. And it still doesn't. If you read the NASA briefings, the European Space Agency white papers, the press cycle that followed the Decadal Survey in April 2022, you will hear the same handful of phrases. Ice giant exploration, completing the tour of the outer planets, understanding planetary formation, filling a critical gap in our solar system inventory. Every word of that is technically true, and every word of it is emotionally misleading. Start with the phrase, ice giant. It sounds soft. It sounds like a frozen world you could imagine standing on, somewhere cold but recognizable. That is not what Uranus is. Uranus is 14.5 Earth masses of hydrogen, helium, water, methane, and ammonia, crushed under its own gravity into a state of matter that has no everyday name. The interior is not ice. It is a hot, dense, electrically conductive fluid, a superionic soup at pressures where water molecules stop being water and start being something the laboratory can only briefly approximate. The cloud tops sit at minus 224 degrees Celsius. That is the coldest planetary atmosphere ever measured in our solar system. Colder than Neptune, which sits 1 billion kilometers farther from the Sun. Translate that number. At minus 224, nitrogen, the gas you are breathing right now, the gas that makes up most of Earth's atmosphere, would fall as snow. And Earth at that temperature would still be warmer than Uranus. Now look at the word exploration. Exploration implies a destination, a surface, a place a probe can reach and then report from. Uranus has none of those things. There is no ground. There is no shoreline between atmosphere and crust. The gas thickens, the pressure rises, and at some point, somewhere around 1,000 kilometers below the cloud tops, the atmosphere stops being gas and becomes something the engineers call a supercritical fluid. The probe does not land, it falls. It transmits data for as long as its structure holds. Then it is crushed, melted, and absorbed into the body of the planet itself. That is the successful outcome. That is what mission planners are working toward. A controlled descent into oblivion, 90 minutes of telemetry, and then silence. Read the press release one more time. Ice Giant Exploration, completing the tour of the planets. Now read the engineering documents. Entry interface at 22 kilometers per second. Heat shield ablation peaking at solar surface temperatures. Probe destruction at 1,000 atmospheres of pressure. These are not the same sentence. They are not even the same language. The press release calls it a flagship mission. The engineering documents call it a one-way descent. That gap between what the public is told and what the hardware is built to do is where the rest of this story lives. Every planet in our solar system spins on an axis that tilts a little. Earth tilts at 23.5 degrees. That tilt is what gives us seasons. Mars tilts at 25, Saturn at 27. Even Jupiter, the giant, tilts only 3 degrees off vertical. These are wobbles, small deviations from upright. Uranus is tilted 98 degrees. That is not a wobble. That is a planet lying on its side. Uranus does not spin like a top. It rolls along its orbit like a ball pushed across a table. Its poles point at the Sun and then point away from the Sun on a cycle that takes 84 Earth years to complete. And here is the part you should sit with for a moment. For 42 of those years, one hemisphere of Uranus faces the Sun continuously. The other hemisphere faces absolute darkness. There is no sunrise, there is no sunset. There is only a season the length of a human life. Now think about how a planet ends up this way. Planets form spinning roughly upright because they accrete from a rotating disk of gas and dust. The disk has an orientation. Everything that forms inside it inherits that orientation. So when you find a planet rolling sideways, you are not looking at a quirk of formation. You are looking at the survivor of something violent. The leading hypothesis is a collision, not a small one. A body somewhere between 1 and 3 Earth masses, a planet-sized object, striking Uranus after it had already formed. Recent simulations from 2018 and 2020 suggest it may have taken 2 impacts to produce the configuration we see today. The math has to fit one specific constraint. The moons of Uranus orbit in the same plane as the tilted equator, in the same prograde direction. That means the impact had to come after the moon system formed, or the moons had to be reassembled from the debris. Either version is catastrophic. This was a violence so large it did not just tip the planet over. It almost certainly disrupted the entire internal structure of the body that survived it. The heat transfer system, the convection currents that should be moving energy from the deep interior to the surface. The dynamo that should be producing a clean dipolar magnetic field. All of it, scrambled by an impact we cannot fully reconstruct, but cannot explain the planet without. Which brings us to the part that should bother you. Every gas giant in our solar system radiates more heat than it receives from the Sun. Every one. Jupiter, Saturn, Neptune. Leftover energy from formation still leaking outward 4.5 billion years later. Except Uranus. And no one knows why. The number is 1.06. That is the ratio of energy Uranus emits compared to the energy it receives from the Sun. For Neptune, the same ratio is 2.6, Saturn around 1.8, Jupiter 1.7. These are planets glowing with leftover formation heat, slowly releasing 4.5 billion years of stored thermal energy into space. Uranus is doing something else. Uranus is, within the precision of our measurements, in thermal equilibrium with sunlight. It has no detectable internal heat output. That should not be possible. A body that large, formed by the same process as Neptune, made of roughly the same material, sitting in the same outer solar system, it should be glowing. The fact that it is not glowing means one of three things, and none of them are comfortable. Option 1. The collision that tipped Uranus on its side also vented its primordial heat. The impact was so energetic that it cooked off the upper layers and let the deep interior cool faster than physics normally allows. Option 2. The interior of Uranus is compositionally stratified, layers of different densities so stable that convection cannot move heat upward. The heat is still down there, it just cannot escape. Option 3. We are looking at Uranus during an unusual moment in its thermal history, and the planet is doing something time variable that our snapshot cannot capture. Each of these hypotheses has a problem, because a planet without internal convection is a planet without a working dynamo, and a planet without a working dynamo should not have a magnetic field. Uranus has a magnetic field, a bizarre one, offset from the center by a third of the planet's radius, tilted 59 degrees from the rotation axis. The mechanism that should produce a magnetic field is missing. The field exists anyway. Compare this to what we understand. Earth's magnetic field comes from molten iron convecting in the outer core. Jupiter's comes from metallic hydrogen circulating under enormous pressure. Saturn's similar. These are mechanisms we can model. Uranus's field appears to come from a thin shell of ionic water, or possibly superionic ice somewhere in the outer mantle. We are not modeling this, we are guessing. Here is why that matters far beyond Uranus. Every model we use to interpret the more than 5,000 exoplanets we have discovered assumes we understand how planetary interiors generate magnetic fields. We use those models to assess habitability, to predict atmospheric retention, to classify worlds. If we cannot explain the planet next door, we cannot trust what we think we know about the planets around other stars. There is a comfortable assumption people make about deep space missions. We sent probes to Jupiter. We sent probes to Saturn. Uranus is just farther out. So a Uranus mission must be the same problem, scaled up. More fuel, longer trip, same playbook. This is wrong in a way that breaks the math. Start with distance. Uranus sits 2.9 billion kilometers from Earth at closest approach. Light, which crosses our entire planet 7.5 times every second, takes 2 hours and 40 minutes to make that trip one way. A command sent from mission control to the orbiter, and the orbiter's response coming back, is a 5-hour and 20-minute conversation. You cannot fly this spacecraft. You can only suggest things to it and wait. Now look at power. Solar flux at Uranus is 1/400th of what it is at Earth. 1/400th. Solar panels, which power almost every modern spacecraft, are useless out there. The mission requires a radioisotope thermoelectric generator, plutonium-238, the isotope that powered Voyager, Cassini, Curiosity, and Perseverance. The United States currently produces roughly 1.5 kilograms of plutonium-238 per year. The Uranus mission needs approximately 30 kilograms. Do the arithmetic. The fuel supply takes most of the time before the launch window just to manufacture. Then look at cruise time. Cassini took 7 years to reach Saturn. Voyager 2 took 8.5 years to reach Uranus on a brute force trajectory in the late 70s. The new mission, depending on the gravity assist available, will take somewhere between 13 and 15 years just to arrive. The principal investigators designing the instruments today will be retired before the probe reaches its target. The graduate students who will analyze the first data are currently in middle school. Compare this to other benchmarks. Apollo 11 launched, landed on the moon, and returned home in 8 days. The entire Apollo program, from Kennedy's speech to the final landing, took 10 years. The Uranus mission, from approval to first data, will take longer than Apollo from start to finish, for one planet, one orbiter, one descending probe. This is not exploration in the way the word is normally used. This is intergenerational logistics, a relay handoff between scientific careers. The people who design the mission are not the people who fly it, and the people who fly it are not the people who interpret what it finds. And once it arrives, after 13 years of silence, after a decade of solar system loneliness, the probe has to do something no spacecraft has ever survived doing. Picture the moment. The orbiter has been in cruise for 13 years. It approaches Uranus on a trajectory shaped by gravity assists from Jupiter and the Sun. Months before arrival, it releases a smaller vehicle, the atmospheric entry probe. A cone of metal and ablative material, roughly the size of a small car, falling toward a planet that has never been touched by anything human-made. It hits the upper atmosphere at 22 kilometers per second. That is roughly 14 times the muzzle velocity of a high-powered rifle. The probe is not flying. It is being shot into the planet. Peak deceleration during entry is somewhere between 200 and 300 grams. A human at 200 G is not injured. A human at 200 G is liquefied within milliseconds. Internal organs torn loose from their connective tissue. Blood vessels burst at the cellular level. The probe survives this only because it is built around a heat shield specifically engineered to absorb the energy of that deceleration. The shield itself reaches temperatures hotter than the surface of the Sun. For several seconds during peak heating, the outer ablative layer is glowing at temperatures exceeding 5,000 degrees Celsius. Material burns away in controlled layers. Each layer carries heat with it as it ablates. Then the probe decelerates. The heat shield is jettisoned, parachutes deploy, and now begins the part that no one outside the planetary science community ever describes in detail. The probe falls for 60 to 90 minutes through the atmosphere of Uranus. First, the upper haze. Then a layer of methane clouds, which is what gives Uranus its pale blue-green color, and what makes it impossible to see the deeper structure from orbit. Then hydrogen sulfide clouds. And yes, you read that correctly. The upper atmosphere of Uranus smells like rotten eggs. Spectroscopy from ground-based telescopes confirmed it in 2018. Below those, ammonia clouds. Below those, water clouds. And below those, the transition zone where the atmosphere stops behaving like a gas and starts behaving like a supercritical fluid, neither liquid nor vapor, both at once. The probe transmits all the way down. Pressure climbs. Temperature climbs. Around 1,000 kilometers below the cloud tops, pressure exceeds 1,000 atmospheres. Temperature exceeds 1,000 degrees Celsius. The probe is crushed, melted, absorbed. This is what touching Uranus actually means, not a handshake. A controlled cremation of our most expensive scientific instrument in exchange for 90 minutes of telemetry from a place no human eye will ever see. And the data it sends back may not be the data we want to hear. Step back from the spacecraft for a moment and look at the infrastructure required to make it exist. You will find a story almost no one tells. The Uranus mission is bottlenecked not by science, not by engineering ambition, not by political will. It is bottlenecked by a single isotope produced inside a single facility in Tennessee, on a timeline measured in grams per year. Plutonium-238, the fuel that lets spacecraft operate where the Sun cannot reach them. The United States stopped producing it in 1988. For almost 3 decades, deep space missions ran on a Cold War stockpile, a dwindling reserve of material manufactured by the same weapons production infrastructure that ended the 20th century. By 2009, the supply was nearly gone. Oak Ridge National Laboratory began a restart program. As of the most recent public estimates, Oak Ridge produces somewhere around 1.5 kilograms of new plutonium-238 per year. The Uranus mission needs approximately 30 kilograms. Compare that to Cassini, which carried 32.7 kilograms, and that supply came from the old stockpile. We are no longer that country. We have to manufacture the fuel 1 gram at a time in a single facility, while simultaneously fueling Mars sample return, Dragonfly to Titan, and whatever else the planetary science community is trying to launch this decade. Now add the launch window. To reach Uranus in 13 years instead of 20, the mission needs a gravity assist from Jupiter. That assist requires Jupiter to be in a specific position relative to Earth and Uranus, and the geometry only works once every 12 to 13 years. The 2032 window is the next one. Miss it, and the alternatives are brutal. Either a much larger and more expensive launch vehicle, or a cruise time stretching past 20 years, or waiting until the mid-2040s for the planetary geometry to align again. This means the mission is not just expensive, it is fragile. A reactor shutdown at Oak Ridge, a budget cut from a hostile Congress, a 6-month schedule slip from a contractor. Any one of these, and the launch window passes. And once it passes, the mission does not get rescheduled to next year. It gets re-evaluated, re-debated, and probably cancelled. This is the part the press releases do not mention. The Uranus mission is being assembled inside a supply chain that did not exist a decade ago and barely exists now. The viewer's grandchildren may never see Uranus up close because of a fuel shortage that gets decided in a congressional subcommittee with 12 people in the room. Which raises the question, why is the official messaging still so calm? Read the decadal survey carefully. The phrasing is precise. Highest priority new flagship mission. Significant scientific value. Critical gap in our planetary inventory. These are the words of an institution choosing every adjective for political durability. Now compare that language to what planetary scientists say at conferences. The tone shifts. The urgency rises. You hear phrases like once-in-a-generation opportunity, narrow window, irreversible scientific loss. The Uranus community, the people who have been studying this planet from a distance for 4 decades, are not calm. They are scared the mission will slip. So why the gap between the public tone and the internal tone? Because urgency in public means panic, and panic in NASA's budget environment means competition. Mars sample return is currently running over budget by billions of dollars. Artemis is consuming a significant fraction of NASA's human spaceflight allocation. If the Uranus mission is described publicly as desperate, it becomes a target. If it is described as exciting, it becomes a program. The softening is not dishonesty. It is institutional self-protection. This pattern is not new. The same dynamic appeared before the Hubble servicing missions. Engineers internally knew the telescope was failing. Public messaging stayed optimistic until the fix was funded. JWST went through a decade of overruns, described publicly as challenges and internally as crises. Voyager's extensions were always framed as bonus science, when the truth was that the team was fighting to keep the spacecraft alive on a shoestring budget. Every time, the internal urgency was real. Every time, the public framing was decorated. The viewer is being managed, not maliciously, managed. NASA has learned, across 60 years of public funding, that missions described as necessary get defunded, and missions described as exciting get approved. So the necessary missions get described as exciting. This is not a conspiracy. It is the rational response of an institution that has watched its budget priorities shift with every administration since 1969. Let me be clear about what I am not saying. I am not saying NASA is lying. I am not saying the scientists are being dishonest. I am not saying the mission should be cancelled or that the framing is corrupt. I am saying that the audience, you watching this, deserves to read between the lines. The fact that the press release is calm does not mean the situation is calm. It means the institution needs your continued support and has learned that calm framing earns that support more reliably than honest framing does. Because what we find at Uranus may not just rewrite a textbook, it may rewrite something much larger. Here is the part that most viewers do not know and that changes the meaning of everything in the previous 8 chapters. The Kepler Space Telescope between 2009 and 2018 surveyed a small patch of sky and confirmed thousands of exoplanets around other stars. When the statistics were tallied, one result stood out and has not gone away. The most common type of planet in the galaxy is not Earth-like. It is not Jupiter-like. It is the class astronomers call sub-Neptunes, worlds between the size of Earth and the size of Neptune, roughly the same family as Uranus. Sub-Neptunes outnumber every other detected planet class. They are not rare, they are not exotic, they are the default. Most of the planets out there, around most of the stars, are some version of the planet we have spent 40 years not looking at. Now connect the dots. We cannot explain Uranus. We cannot model its interior. We cannot account for its missing heat. We cannot reconstruct the mechanism that produces its magnetic field. And the kind of planet Uranus represents is the most common kind in the universe. Every claim you have read in the news about a potentially habitable world, every artist's rendering of an exoplanet atmosphere, every paper modeling the chemistry of a transiting sub-Neptune, every search for biosignatures on a distant world, all of it rests on physics we cannot verify by looking at our own example. We are extrapolating outward from a foundation we have not built yet. Compare this to medicine. Imagine if the most common disease in humanity was also the one disease the medical community had never studied properly, because the patient lived next door and seemed boring. Imagine if every drug approval, every treatment protocol, every clinical trial design assumed an understanding of that disease that no one actually had. That is, structurally, what planetary science has been doing for 40 years. The radius valley, the mass-radius relationship, the atmospheric retention models, the habitability assessments. All of these depend on understanding sub-Neptune interiors. And our nearest sub-Neptune is a planet whose interior we have not measured, whose magnetic field we cannot model, and whose thermal history we cannot reconstruct. So when the probe finally arrives at Uranus in the late 2040s, what we are really asking is not what is Uranus made of. We're asking how wrong we have been about everything else. About every planet in every Kepler catalogue. About every habitable zone calculation. About every search for life beyond Earth that depended on a planetary physics we now suspect is incomplete. The stakes are not local. They never were. Let me bring this back to the beginning. January 1986, Voyager 2 crosses the magnetosphere of Uranus at 14 kilometers per second. 6 hours of usable data. A planet tilted 98 degrees, a magnetic field offset from its center, a thermal signature that did not match any model. The team thought the instruments were broken. They were not. We packed up the data, moved on to Neptune, and did not return. 40 years. 40 years during which we discovered that Uranus represents the most common class of planet in the galaxy. 40 years during which the magnetic field anomaly was never explained. 40 years during which the missing internal heat became more inexplicable, not less. 40 years during which the impact that tilted the planet remained a hypothesis with no direct evidence. 40 years during which every textbook image of Uranus was built on those 6 hours of confused data from a probe flying past. Now consider what is on the table. a 2032 launch window that closes once and does not reopen for over a decade. A plutonium-238 supply chain that produces grams per year against a mission requirement of kilograms. A 13-year cruise time that means most of you watching this will be receiving Social Security before the first data arrives. A probe whose successful mission is its own destruction. An exoplanet catalogue whose foundations cannot be verified until we go. This is not a fun story about a planet with a silly name. This is one of the most consequential missions of the 21st century, and it is being treated by the public as a footnote. The illusion I want to strip away in this final chapter is the illusion of time. We do not have time. The 2032 window is real. The fuel bottleneck is real. The institutional fragility is real. If this mission slips past the launch window, it does not get rescheduled to 2033. It gets re-evaluated, re-debated, deprioritized in favor of louder competitors, and quietly absorbed into a list of things we will eventually do when conditions improve. Conditions do not improve, they erode. Here is the narrow hope, and you have earned it by sitting through this. The mission is funded. The probe is being designed. The window is still open, for now. The fact that anyone outside the planetary science community is paying attention, the fact that you watched this video to the end, is itself a small contribution to whether this mission survives the next budget cycle. Public attention is currency in this field. It is the only currency that matters between decadal surveys. Voyager 2 flew past Uranus in 1986 and never came back. The planet has been waiting, sideways, for 40 years for us to admit we got it wrong. The universe has been patient with our inattention. The bill is now due.